So let's take a look here at this second example. So this one says a rectangular box without a lid is to be made from 12 meters squared of cardboard. What is the maximum volume of such a box? So this is another example of a typical optimization problem. This one is in a sense even more typical because, we are given very little information. Compare this to the problem we just worked on, where there was quite a paragraph of lead up and context to go along with it. So here we are given very little information, but believe it or not, we have everything we need. So I'm going to follow the procedure that we've been talking about in this video. First thing I will figure out is what is the objective function. And I go back to the statement of usually where the question mark is, what is the maximum volume, right? So that's our objective function. So max volume. Okay, so I still haven't mathematized that. I don't know what the mathematical expression for it is or what the variables are. That will come in time. Number two, I want to draw a diagram. So this is, I'm told, a rectangular box without a lid. So I'm going to draw a rectangular box without a lid. So there we go. That is my rectangular box. And it has no lid. So, it's just the sides and the bottom of the box, but not the top. All right. And then I'm going to start drawing variables and trying to figure out, mathematize the things that I'm trying to find. There is a constraint, so I'll get there in a minute. So what are the variables? So the volume of this box is the length times the width times the height. So I'm just going to label variables here. Excuse me, x, y, z. So that is the volume. So I'm going to go back to my objective function, and I'm going to replace it with maximize the volume. And the volume of this box, since it's a rectangular box, is just length times width times height. Great. So now let's talk about the constraint. So I'm just going to scroll back up to our procedure just to double check where we are and where we are going to head. So we have found the objective function. That's the volume of the box. Great. We drew a diagram and we determined the relevant variables, x, y, z. And now we are going to extract the constraints and then the domain. All right, so let's scroll back down. So number 4, constraints. Well, we are told that it's to be made from 12 square meters of cardboard. Again, this is where I had mentioned earlier in the video, you want to use the context to help you figure out what type of constraint this is and how to mathematize it. Here, the units give you a big clue, square meters. So those are units of area. And just if you think about it, you have this giant block of cardboard, and then maybe you want to slice it up in some way, right, to create a box. And that's going to create a square-looking box. We want a rectangular box, so maybe you want to slice it, in different ways so that, some of the parts of the box are longer than others. The point is you start with an area, and from that you actually cut it out to make a box. So this is a constraint about the area, surface area that we have for the box. And if we start counting surface area, let's first look at this face. This has length x and height z. It's the same one as this one. So that is x, z, and there's 2 of them. Plus, 2 of them, the front one and the back one. And then we start counting surface area the other way. So we have the bottom of the box. That surface area is x, y. The box doesn't have a lid, so we're not going to put a 2 there. And then we have the sides. So we have this right here. And that area is y times z. And there's 2 of those. So we have plus 2yz. And that should equal the constraint, which is 12 in this case. Great. So we have our constraint. We have our objective function. And then we are going to head next to try to figure out the domain. So in this step, I usually also try to substitute in the domain or the constraint, if there is one, into the function to simplify it. So how am I going to do that here? I'm going to notice that these have a z in them. So I'm just going to factor out a z, 2x plus 2y, and then move over this term. So that's 12 minus xy. And then I will solve for z here to get me to this point. Great. So that is my z value. And I'm going to take that and then plug it in here. to express the volume as a function of only x and y. So xy stays, and then I have this z over here, where I've now factored out the 2 in the denominator from here. Great, so this is my new version of the objective function. And this is my constraint that I'll be looking at up here, or viewed another way, this is the z dimension of the box. So what about domain, right? How do I start thinking about this? First of all, in this iteration, right, x and y are still part of the box, the dimensions of the box. So we want there to be an actual box, so we want these to be positive numbers. And then as a function, if I look at this v function, I have a denominator. So I don't want the denominator to be 0. I also don't want the denominator to be negative. Again, we would have a negative volume. So what I want is x plus y to be bigger than 0. And up here, another thing that I don't want is I don't want 12 minus x times y to be less than 0, to be negative, or to be equal to 0. So I definitely want this to be bigger than 0. Now there is, a question here that really what we want is 12 minus xy, this whole thing. I want this whole thing to be bigger than 0, right? But notice that, again, because I don't want to have a negative pop out of this, negative number or 0. That would give me a negative or 0 volume. But notice that if I want this to be bigger than 0, then, two things happen. If x plus y is positive, which it should be because I don't want a negative number in the denominator, then when I multiply both of these inequalities by x plus y, I get this one. So these really the two inequalities that we've come up with are really two independent inequalities. And you can see that actually one of them is superfluous, because if I demand x and y both being 0, then their sum being positive, then their sum is going to be positive. So I actually don't have to worry about this inequality. We can disregard it. This one I still do have to worry about. Even if x and y are both positive, this inequality tells me that the product has to be less than 12. There are many, many pairs of positive numbers whose product is greater than 12. For example, 12 times 12. So that is a legitimate restriction. So if I were to plot or visualize my domain then, these two tell me that I am over here in the first quadrant of the plane, positive x, positive y. And then if I go ahead and divide by x here, which I can do because I know that x is positive, excuse me, then I get a graph whose portion in the first quadrant looks like that, 12 over x. And I want it to be less than 12 over x. So I'm going to do the same thing I did in the previous example problem and kind of put a dashed line to remind ourselves that we do not want to be on this graph. So it seems like everything, again, in the interior here is my domain. So now we think about this and we say, is this closed, bounded? Which type of optimization procedure do I follow? The answer here is that this is not a bounded set. You can see that this function is going to fly off to infinity. This should kind of make sense, although in a realistic way, we're not going to make a box that has x, I believe this was the width, 0.000001 meter long or something, right? So there are limits, and this is actually going to come in handy a little bit later on in this problem when we justify, how we arrive at the fact that there's going to be only one real point for us to look at, only one critical point, which will yield the maximum volume. So at this point, we've looked at the domain. It is not bounded. It is not closed. So this is another example where we are going to hope that there's only one critical point, and that will turn out to be the case. So we're going to go off and find the partial derivatives. The function itself that we found is quite involved. So for the purposes of time and also just to give us a little bit of a break here, I am just going to give you the partial derivatives. Certainly in a context where you might need to do these calculations out, then this is something that you might be given, this information, to speed up, excuse me, the calculation of the extremum. Or you might be given a much simpler function to find the partial derivatives of that you can then do by hand and do it a little quicker. But anyway, these are what the partial derivatives turn out to be. You could also, of course, use a technology to find this, maybe like Wolfram Alpha, for example, which will help you check your partial derivatives work. And now we're off then to find the critical points. So to do so, we set the partial derivatives equal to 0. We'll look really quickly now to make sure that there are no places where the partial derivatives are undefined. Indeed, that would only happen if the denominator were 0. That would require x plus y to equal 0. But as we said on our domain, x and y are both positive. So x plus y is positive. So the only possible critical points are of the stationary point variety, where the derivatives, partial derivatives, are 0. Again, because x plus y is positive, we can multiply both of these equations by the denominator, and they will go away. And then we'll be left with this equals 0, and this equals 0. So if we look what happens there, I have two possibilities here. I either get y squared equals 0, or 12 minus 2xy minus x squared equals 0. And then over here, I get x squared equals 0, or 12 minus 2xy minus y squared equals 0. Again, we reject this one and this one because they imply x and y are 0, and that's not in our domain. There would be no box. And then when we look at these two, we can play the same game that we played in the previous problem, in the sense that these two quantities are exactly the same. So this equation we can rewrite as 12 minus 2xy equals x squared. This equation we can rewrite as 12 minus 2xy equals y squared. Same thing, so these two are equal. So I get x squared equals y squared. Various ways you could solve this. My preferred favorite, so we don't run into any trouble with plus or minus and square roots and things like that, is view it as a difference of squares. And I get x equals y and x equals negative y. Okay. Again, we said that x and y have to be positive. So we're going to have to reject this possibility because that leads to at least one of these being negative if the other one is positive. So we're going to get rid of this option, and we are going to keep that option. So now we know that the only critical point, the stationary point specifically in this problem, is such that x equals y. And then I'm going to take that and plug it into any one of these. So, let's do y equals x usually, as we usually do, and plug it into that one. What results? I get 12 minus 2x squared, because it's y equals x, equals x squared. I rearrange things here. I get 3x squared is 12. X squared is 4. I have technically two solutions, negative 2 and 2. But once again, I don't want negative numbers that are outside of my domain. So I stick with x equals 2. And finally, we have found a numerical value for x. We know that x and y are the same. So I have a numerical value for y. Awesome. And then let's just go back and calculate very quickly what is the volume of this box with a side length of 2 meters and then a length times width of 2 meters and 2 meters. So if I go back to the volume function, there it is, and I substitute in 2 comma 2, and I do all the math here on the right hand side. Again, I'll save you that arithmetic. I get 4. Okay, so this is something that you can check. All we've done so far is we've found the stationary point, and we have found the output, the z-value of that stationary point. But now we're going to make the usual arguments that we make, right? So we are going to say, wait a minute. Actually, I'm going to introduce you to a new argument. But we're going to say, wait a minute. This is the only stationary point that we found in our domain. Great. So there's only one critical point. So we are going to hope that this critical point is our maximum. is a local maximum. Because if it is a local maximum, it has to be the absolute maximum. If there was another place that could be higher than it, then that would have shown up as a critical point. You might again worry about the boundary, but you can imagine a function that has a local maximum, maybe like that right there. If somehow over here, way out over here, is the boundary, let's say, and the function has a point that's higher, then, first of all, what does it have to do? It has to turn around to reach that higher point. Again, continuity is working in the background for all of these functions that we deal with. So if this function were to actually turn around, we would detect another critical point somewhere. So this is really just another reiteration of the same argument that comes from Calculus 1 that you're familiar with, that if there's only one critical point and the function you're looking at is differentiable, it's nice, it's continuous, and you find that critical point is a local something, it is an absolute same something. So how do we show then that this is a local maximum so that it makes it an absolute maximum? We have many of the same options that we had before in the previous example. But now I'm going to add a fourth one, and I'm just going to call this real world context. And the real world context is this. I had 12 square meters of cardboard, and I cut that up and made it into a rectangular box, right? So I can make all sorts of, types of rectangular boxes. I can make really tall and thin ones. I can make really, really flat looking ones that are not so high, right? I can make lots of options. And each one of these will have a positive volume associated with it, okay? They all will have a positive volume because they are a box, right? It exists and the box has a volume as opposed to zero or certainly a negative volume. So from a physical point of view, all these generate for our purposes z-values. And as I go, for example, from here to maybe considering this, the z-value will change. It's still a positive number. What we're interested in this problem is whether the volume goes up, because then this box can fit more stuff than this box. And then maybe we go from this box to this box, and maybe the volume goes up. I doubt it, given the pictures, but perhaps. So the point is that we're dealing with a bunch of positive numbers that are for the volume function, and there is going to be clearly one box, maybe it's this one among these three that looks most reasonable, which has a largest positive number. So this is a physical argument. So this is using the real world context of the problem, knowing that there is a box with a maximum volume, given that there's all sorts of different boxes we could construct, which we have all reason to suspect have different volume values, and that these are all positive numbers. So this is the argument that I'm going to take here, just to again expose you to a different way to make the case. Once again, you can always, I think the first one I had put here on the earlier problem was second derivative test. You can try that. You can also take a look at the graph, and there may be some algebraic ways, although this function is quite difficult to work with algebraically, but there may be some algebraic ways to convince yourself that in fact there is a maximum. Okay, so that's what we've done so far in terms of arguing for the absolute maximum, and that would make this the location in terms of a graph of the absolute maximum. That would make this the actual absolute maximum itself. So I always like to go back to the problem that was given and make sure I answer it the way that it asked. So what is the maximum volume? So they didn't want us to find the dimensions of the box of maximum volume. They wanted us to actually find the maximum volume. So the actual answer to the question here posed would be 4. And to wrap up this video, I'm going to switch over then and show you what this graph looks like in 3D. So here it is plotted over here on the left-hand side. Oh, let me stop its rotation. Plotted over here on the left-hand side. and this is the function. This was the one left over from the previous problem. And I will soon show you where the maximum is that we just calculated. X equals 2, y equals 2, z equals 4. But you can see indeed, you know, in a mathematical way, what I was arguing earlier about just what we know about cutting and gluing and making boxes from cardboard. Each one of these points on the function represents the volume of a box that was created from 12 meters squared of cardboard with an x value of 2 and a y value, or an x value of, you know, wherever we are at the point, and a y value of wherever we are at the point. So again, this is a physical manifestation of that fact that you can make boxes of all sorts of dimensions. And among them, there's going to be a maximum. So one thing to mention down here, you know, you see the program trying to do its best. I cut it off at z equals 0 because that's when we start not having a box. You can see the program trying its best to deal with all of the divisions here that are getting close to 0. So let me now then activate the point 2, 2, 4, and you can see it just pops up right at the very tip top of this surface. And you can move around and kind of see that this is indeed at the top largest z value here. So you can look at it from all sorts of different perspectives. That is the largest value, the maximum, absolute maximum that we found. And if you look at this in the xy plane, you can get some sense of, to illustrate the last thing I want to here, some sense of the domain that we were talking about, right? It looks like x can go off as positive as you would like, y can go off as positive as you'd like. You know, I restricted, I'll show you over here, the domain of the function that I plotted, just to look at one small slice of it. And then you can see kind of here emerging the top curve that we saw, 12 over x, right over here. Great. And then very last thing that I will mention for this function is that this is a good example of a function that you can play around with in terms of changing the constraint. So, you know, if we go back to the notion of 12 meters squared, that's not magical. You know, you could change this to 5 square meters. You could change it to 10 square meters. The number there really does not matter. It won't affect the existence of this absolute extremum and the existence of it being the only, you know, at the only critical point. So great. So this has been enough of a long video that we've covered a lot, and my small reminder is that optimization problems were one of the pinnacles of single variable calculus. They took a long time and they were tricky for all sorts of reasons. They required you to remember a lot of things and apply them in new contexts. Expect optimization problems in this multivariable context to have much the same features. But as with all things, practice, practice, practice will help you. So I highly encourage you to work through some of the practice problems suggested on the website, and also to use these applets and perhaps other resources to help you just visualize what these extrema look like. And I'll see you in the next lesson.